All right, welcome to part 8 of robotic arm manipulation with human experiences in HRL. In this video, we're going to go ahead and get into the meta agent, which will be sort of the master agent in charge of controlling the various sub-agents and getting them to, choosing which agent to pick for a particular task. Now, in real hierarchical reinforcement learning, or what I think most people would consider it, there is some kind of actual RL model that's running the show, that's in that top level role. In this implementation, that's just going to be a static policy, and there's a couple reasons for that. One, I wanted to keep this a little bit simpler than it would have been if I tried to tackle a full top level model making decisions type of implementation. This is already long and fairly complex, but also because it wouldn't have added a tremendous amount of value. The list, we're going to be passing in a task list, and if I had trained an agent to choose what tasks to accomplish, what task to select in that task list, it actually would have been a fairly basic classification problem. I don't think it would have added anything to the solution. HRL, real, full, an agent controlling many sub-agents, I think makes a lot more sense in situations where maybe you have a high-level agent that's taking map directions and trying to get a car across town, and a low-level agent that's in charge of keeping it in the middle of the road might be a good example. In this scenario, with a static list of potential to-dos, there's just not a ton of value in training, some sort of high-level model. So what we're going to be doing is we'll be building a static policy that selects, fairly static. It will select the appropriate agents based on a list of tasks passed into the policy and go do what it needs to do to accomplish them. Now, if you're in this video, you should have gotten through the last one where we went ahead and trained all of our individual agents. I'm assuming walking into this that you have taken the time to go through, either generate data or download my data for each one of these, or for, at minimum the 3 high-level tasks, microwave, hinge cabinet, and top burner, and that you have trained 3 agents that are capable of accomplishing those tasks. You should have a policy microwave, a policy hinge cabinet, and a policy top burner. If you don't have those, if those aren't working yet, then the next step of this won't work either, and you should go back and get that working. This is also a good part to say, and I think I covered this earlier in the series, but your data is very, very important for this one. Once you've got your pre-train information, you're going to be post-training. We're going to start by creating the meta agent and testing the meta agent, but then we're also going to train all of these things together as part of the meta agent. And the reason we do that is that it, all of these are trained starting from the starting position, starting from where the robot arm is when it's dropped into the environment. And if you just go and run it out of the box, you're going to get some success. You'll get about 70% success, but it gets stuck moving from task to task. It'll open a cabinet and then not know how to get to the microwave. Even though it's moved to the microwave policy has never seen the arm in a position next to the cabinet. So we've basically gone through rough training of teaching each policy. But then as we get into the meta agent, we're going to be doing some fine-tuning, and that fine-tuning isn't going to include building a buffer of experiences that are coming from all of the agents together. So we'll go from training on one agent to training on data from all of the agents as they flow together. And this will make more sense as we get into coding it. But the reason I brought all this up now is that when we get to that fine-tuning phase, if we make a mistake, if we do something wrong the first time, or just do a run and don't finish it, it is going to break the data for the models that you've already trained. It could leave them in a half functional state that might be hard to get back from. So this is a great time, if you've got your working models, to go and copy checkpoints to checkpoints_pretrain or something that you can then copy back from if any of these models gets corrupted. In fact, I've found it's been best to just go ahead and every single time I run the meta agent training, to go copy from the original data, so that I've always got a clean starting place. So that is my warning. Save your data, unless you want to have to go and retrain all of these models again, which I doubt you do. So let's go ahead, and we're going to start working on the meta agent. This is going to be metaagent.py. And right off the bat, we are probably going to need a lot of the imports from agent.py. So let's just go ahead and pull those over. We will also need random. And then we can start to define our meta agent class. So class, give myself one more space. Class meta agent, object definite. Go ahead and declare our init method. And here we will have self env, and we'll tell it it's of type RoboGym observation wrapper. Goal list, because remember, we're not just taking in one goal, we're taking in a potential list of goals, although I'll default that to microwave. Replay buffer size, we'll make that 1,000,000. And max episode steps will default to 500, and then we can remove this none over here. And then for the init method, we're basically going to be declaring dictionaries of agents, dictionaries of memories. That's, and then we'll be using those dictionaries to select the appropriate policies based on the task at hand. So we'll say self.agentDict equals, and then self.memdict, and I'm going to say this is a dict str replay buffer. This part's not required. I just found that it was helpful to tell my editor what it was. We'll do a goal list no spaces, and we're going to use a list comprehension here. We'll do a.replace, replace spaces with underscores for a in goal list. Okay. We'll do self.goalDict, and again we're going to tell it it is a dictionary of str equals dict zip goal list no spaces goal list. So we're going to use goals without spaces. So for example, hinge_cabinet is the goal with no spaces. So we're going to use that as a primary key in the various things that we're going to be doing in this class. So in order to do that, we need, we're going to be you're going to see a couple things where we've got our goal list without spaces zipped with some other value as we go through this. Maybe not directly using zip, but paired with other values. So we'll do self.env equals env. We'll do self.agent equals none. And we may have to import agent from agent import agent. Okay, now it's happy. We'll do self.replay buffer size is equal to replay. It doesn't like something in my list here because it's not autofilling replay buffer size. So let's see. I'm guessing it's a missing comma, or it's something in the syntax that it doesn't like. Let's get rid of that. See if it still doesn't like it. So it thinks I have an unclosed parentheses there. But I'm not entirely sure why. Yep. Paren was not closed. Okay. Yeah. Well, I don't see it right off the bat. We're going to keep, we're going to type out the rest of this and then try to figure it out. Replay buffer size. Self.max episode steps equals max episode steps. All right, and I think I see the problem. Right here, I've got goal list microwave as if I'm indexing microwave, and I need to do goal list equals microwave, and then everything is happy. Okay. We need to initialize our memory buffers. So we're going to say def initialize memory self augment rewards equals true. Augment data will just default to true. Augment noise ratio equals 0.1. And then we'll say for goal in self.goal_dict self.env.set goal. And then we'll do self.goal_dict goal. So indexing self.goal_dict at goal is going to give us the goal with the spaces. So then we are going to do observation info equals self.env.reset. Something I ran into after getting into this is that the way we wrap the environment, and this was probably a mistake to implement it this way, ended up resulting in slightly different observation sizes for the various goals in the environment. So, microwave and cabinet might not have the same observation size. So that's going to cause us a couple of problems, both of which we can solve, but it does mean that for each one of these, we need to actually reset, and then using that observation, we're going to get observation size equals observation.shape 0. And then we'll be using that to declare our replay buffer. So memory equals replay buffer, self.replay buffer size, input size equals observation size, and actions equals self.env.action space.shape. Augment rewards equals augment rewards. Augment data equals augment data. Expert data ratio equals 0. Augment noise ratio equals augment noise ratio. And then finally, we'll say self.memdict. We will use goal as our index equals memory, or our key. I guess it wouldn't technically be an index there. All right. We need to declare our load memory class, or load memory method. So def load memory self for buffer in self.memdict self.mem.dict buffer load from CSV file name equals checkpoints / human memory buffer .npz. And keep in mind, buffer in this case, again, is a key that will equal a goal with no spaces. So that'll grab one of these values. I also need to, I just realized I loaded a fully trained checkpoint for most of mine. So that is not going to be what we want. You don't have to follow this. You don't have these checkpoints. You do if you've been training, but you don't have multiple copies of them like I do. I'm going to grab from my pre-train checkpoints, and I will also get cabinet. All right, back to coding. Let's see, def initialize agents. Similar concept here. Self gamma will default to 0.99. Tau will default to 0.005. Alpha will default to 0.1. Target update interval, we're going to default to 2. Hidden size will be 512. And learning rate will default to 0.0001. Okay. Just similarly to the memory, we're going to do for goal in self.goal.dict. Let me give myself a line there. We'll do self.env.set goal, self.goal.dict goal. Observation info equals self.env.reset. Observation size is equal to observation.shape. Agent is going to be equal to agent. Observation size, self.env.action space gamma equals gamma, tau equals tau, alpha equals alpha, basically just setting all our params. Target update interval equals target update interval. Hidden size equals hidden size. Learning rate equals learning rate. And goal equals goal. Okay. We'll say print loading checkpoint for goal, just to get some output from the process, and then agent.load checkpoint. Evaluate equals true, because this is out of the box. We want to go ahead and set evaluate to we don't want, so evaluate true for load checkpoint basically made it fail if there were no checkpoints. If we have no checkpoints, there's no point in training a meta agent. So we do want that to fail. So we'll say self.agent.dict goal equals agent. That finishes the initialize agents method. Now we need to do a save models method. Save models. And we can rely on, we've built some nice abstractions here. So we can now use those abstractions to not have to, rewrite too much of this. So we can just say for agent in self.agent.dict, self.agent.dict, agent.save checkpoint. You can start to see how most of the things we're doing in meta agent are, just a wrapper for many agents. And then finally, we can go ahead and write our test method. So we can say def test, just take self, action equals none, episode reward equals 0, And for goal in self.goalDict, print attempting goal self.env.set goal self.goalDict goal self.agent equals self.agent.dict goal. So, again, we're telling the environment what goal we're going after, which is what tells it, if you recall correctly, setting the goal is basically what's going to pull the right observation. So this is actually kind of important. So this will change. This will be a dictionary of many potential goals if we pass in an environment that has multiple objectives that the agent can go after. We are explicitly in our metaagent.py telling it that there is one goal we're going after and we want observations for that goal. That is a critical part of having trained all of these things separately, and then using them in concert is that the environment needs to look a lot like it did when we did separate training for it to be successful. Otherwise, it's going to throw it off. It's not going to know what to do with additional data or a different action space or anything like that. So at that point, we've declared our goal. We've gone ahead and we've set the main agent, self.agent, to the agent dictionary for that goal. And now we're just going to run test on it. So action reward equals self.agent.test env equals self.env, episodes equals 1, max episode steps equals self.max episode steps, and prev action equals action. So we're finally at a point where we can talk about why we've got this. We're going to go over to the test method in a moment and look at that. Episode reward plus equals reward, and then return episode reward. So if we go over to agent and we go down to test, I think at the time I said we were passing in this previous action, but I just said that it had something to do with the meta agent, and I didn't really explain anymore. So as this thing loops through, it's going to run against, agent. It's going to start with action none. It's going to run with action none. But then when we loop all the way back around and pick up the next goal, so let's say it's done microwave and now it needs to do cabinet, or swing cabinet, whatever it was called, it's not going to know, it's not going to have anything to base that action off of. And we actually don't want to reset every time, because if you reset, it resets the environment. It doesn't stay in the same environment accomplishing a new goal. So we can't do state reset. So what we have to do is actually say we're going to pass in a previous action. So we're just going to repeat the, whatever the first agent was, the last action it took, we're going to repeat it one time in the next agent load to give the second agent something that it can pick up on and pick up from the first agent. So we implemented most of that logic in the meta agent. We just need to make one change here. So we're going to say if prev action is not none, and here we'll say state reward done equals env.step. So that's us taking the previous action once, else, and then we're good. And then a little bit further down, we are, let me find where we're using, so if reward equals 1, prev action is going to be prev action, and that should put us in a good spot. So this first time we're doing if prev action is not none, then go ahead and grab this else state here, and then we're going into a while loop to actually run the episode. And again, we'll reset previous action if reward equals 1 at some point. So if it achieves a goal. So at that point we should have our meta test.py. So let's go ahead and we're going to create test meta.py. I did find it much easier, again, to just kind of keep all of these top-level scripts kind of similar. So, or kind of, similar but separate, rather than trying to bake it all into one. So I am just going to go and steal the top of test.py and copy it into test meta, because some of those things are going to be the same. Now, instead of task, we're going to have tasks, and this is going to be a list, and it's going to be top burner, microwave, and we'll go ahead and do hinge cabinet. We'll also make max episode steps 1200. We want that to be a little bit different. So we no longer need task no spaces. And then we're going to say live test equals true. We'll be using this a little bit. And we'll say if live test, then go ahead and declare an env equals gem make. Tasks to complete, we can now just turn this into tasks. Render mode will be human. And then we no longer need goal equals task because the meta agent is going to set that. We will do meta agent equals meta agent. Oh, and we have to actually import from meta agent import star. So meta agent equals meta agent. env tasks max episode steps equals max episode steps. And then we really did most of the heavy lifting earlier. So now we can just say meta agent dot initialize agents, meta agent dot test, and env dot close. And this should, if we haven't made any typos or bugs or errors, it should go ahead and run our meta agent. Let's give it a shot. Hey, and it failed. Okay. So let's see what we didn't like. So it raised an exception, unable to evaluate models, which is good. We don't want we do not want that, grabbing the wrong models. So it's saying copying a param with shape torch.size 512 512 from checkpoint. The shape in the current model is torch size 572. Okay, so it didn't like something in my copied over models. So I'm guessing that I probably had something small that was different in my, my model pi in my initial implementation than in the one that I built over here, which is fine. That does happen. So let me go take a look at what that might be. Okay, here I've got linear 1, linear 2, and let's see, which one did it not like? It didn't like linear 5 dot weight. So let me see where I used linear 5. Okay, I see what I did. I had a critic that had an extra layer. You actually do not need to copy what I'm about to do because you are not going to be starting with my models. So I experimented with, here, I'll just pull the original code over. It's a little messier, but that's fine. So I had linear layers 1, 2, 3, 4, 5, and 6 here. And then I ultimately kept 1, 2, 4, and 5, and I cut out 3 and 6. So when I did the walkthrough, I of course just did 1, 2, 3, and 4 because, you know, why would you maintain a mistake in the end code? But now that I'm trying to load my previous models, it is going to cause me some trouble. So you do not have to do this, but I am going to go and copy my critic from my original so that it can pick up the model successfully. And let me make sure, I think I tabbed that over one too many to the right. Again, this is identical. I just had some unused layers in here that did not make it into the final cut, but they are preventing me from, you know, successfully using my pre-trained models. So I'm going to say actor star, or policy star. I'm just going to recopy a few things. And then critic star. Okay. And we'll run test meta again. All right. And we now have our agent successfully doing what you saw in the initial video. It's able to go and open, you know, turn a switch on and open a microwave pretty successfully, and then open a cupboard. Now what I found was with just the pre-training, it was about 75% successful, which is pretty cool. Like just with pre-train, 75% success, really not a bad place to be. And when I say 75% success, I mean when you pass in a list of multiple things, it succeeded about, you know, 75% of the time out of all of the tasks in the task list. So if it got stuck on task number 1, then the whole episode was a wash. If it succeeded 2 out of 3, then that counted as 2 towards the score. In the next video, what we're going to do is go train all of them together. So we're going to go from that 75-ish% success rate to actually training the agents together in the meta agent so that it can get really good at those transitions. And I'm actually kind of suspicious that this is working a little bit better than I expected it to. I'm thinking that I may have copied over some slightly more trained models than I intended to. Hey, there we go. There it is getting stuck. That is the robot that I expected to see. So it opened the microwave, but then it got confused because it had never opened the cabinet, or it does not have training data on opening the cabinet after opening the microwave. So this is actually exactly what I expect to see. I expect a certain amount of the time that it is going to, you know, hang up, get stuck, not know what to do next, because it hasn't trained in going from task to task, and that only gets worse as you add more tasks. So yeah, this is a great place to stop. In the next video, we will go ahead and implement the meta train function, and then we'll also throw together some functions to help us test it a little bit more scientifically than just looking at the agent get stuck here. We'll put together a method that generates some statistics for us, and we'll be just about near the end. So see you in the next video.